So are there any questions or concerns before we pick it up where we left off yesterday? So we are studying logarithmic function, section 5.2 in the textbook. And yesterday at the end of class, I just started to introduce the natural logarithmic function, right? So let's just sort of review a little bit where we ended yesterday. So you know that this is function notation. F is the name of the function, and x is the input variable. So we can let f of x equal a logarithmic function, right? The logarithmic function log base e of x. And you know base e is that special number, right? Roughly equals 2.718. And because it is a special number, it gets its own special name for logarithmic function of base e. And that special name is ln. ln can be thought of as just another name for a function like f, right? F of x, f is the name of the function. Well, this is ln of x. And so it's kind of treated like you would f, okay? So x is the input, okay? ln is the name of the function. But in mathematics, functions that have their own special name, we often drop the parentheses when we're using them. And so in this case, we just write ln of x. So this really means this, okay? So don't let the removal, this is not multiplication. Students sometimes think this is ln times x. That's not the case. This is the name of the function, and this is the input to the function. And sometimes, just a reminder, instead of saying ln of x, I'll say the natural log of x, okay? Because that's how I did it how we did it back when I was an undergraduate, okay? All right, so there are properties of the natural log function, and they are similar to the properties back on page 1, right? So this is page 1 of your notes, properties of the logarithmic function with base a, and these properties, right, from the natural log function are the same as those on page 1, except we replace log base a with ln. Okay. So property 1 for the natural log function is the natural log of 1 is equal to 0. Okay. All I did was replace log base a with ln. Property 2, the natural log of the number e is equal to 1. So I replace log base a with ln and a with e. Property 3, the natural log of e to the x is just x. So all I did was replace log base a with ln and replace this a with e. So we have ln of e to the x is x. Okay? So we're doing the same properties on page 1, except with the new notation, base e. Okay? And the last property, e raised to the natural log of x is just x. In example 6, on the same coordinate plane, sketch the graphs of the following function. F of x equals e to the x, and g of x equals the natural log of x. So you know that exponential functions and the corresponding logarithmic function are inverse functions of each other. Well, that's true here for the natural exponential function and natural log function. The natural exponential function and the natural log function are inverse functions of each other. So, in graphing f of x equals e to the x, now we did a lot of graphing of exponential functions back in section 5.1, right? E, right, is greater than 1, and we know any exponential function with a base greater than 1, the graph goes up from left to right. Okay, remember that? And so when it crosses the y-axis at the point 0, 1. So that's roughly what the graph of e to the x looks like. Okay. So the graph of the natural log of x, right, which is the inverse function of e to the x, it's going to look like that, okay, where it crosses the x-axis at the point 1, 0. So this is the graph of g of x equals the natural log of x. And remember, those two graphs are reflections of each other across the diagonal line y equals x. So that's a graph of e to the x and the natural log of x. And they're inverse functions of each other. Any questions on that? Yes, ma'am.
Can y equals x be like the slant asymptote, or is it just like?
Yeah, no, it's not a slant asymptote.
Okay.
You know how when we were studying symmetry, reflections, it would be symmetric to the y-axis or the x-axis or the origin? Well, these are symmetric to this diagonal line. Okay. Okay. Alrighty. Alright, just as there are rules of exponents, there are rules of logarithms. Now the good news is, right, there are lots of rules of exponents, but there are only 3 rules of logarithms that you have to memorize. And so we're going to write out these rules for a logarithmic function of base A. And we're going to write out these rules for this special logarithmic function, the natural logarithm. And so, in your notes it says n is any real number and u and v are positive real numbers. So if I take the log, base A, of u times v, okay, I'm taking the log of a product, rule of logarithm says this is equivalent to the log of the first number plus the log of the second number. So the log of this product is equal to the log of the first number plus the log of the second number. And with the natural log function, we write this rule as the natural log of u times v is equal to the natural log of u plus the natural log of v. And this is called the product rule. Then the second rule has to deal with fractions. If I had the fraction u over v, log base A of u over v is equal to the log of the numerator minus the log of the denominator. So I can split this log of a fraction into a difference. And so we have something similar with the natural log. The natural log of u over v is equal to the natural log of u minus the natural log of v. And that is called the quotient rule. The third rule says log base A of u raised to the nth power. Okay? So that's u being raised to the nth power. And we're taking the log of u to the n base A. The power rule says I can bring this exponent n down in front of the log. So this is equivalent to n times the log base A of u. And for the natural logarithm, we have the natural log of u to the n is equal to n times the natural log of u. And that's called the power rule. So let's apply some of these rules to the logarithmic, to the expressions on the next page in example 7. So we're going to simplify the natural log of 1 over e. So I can use quotient rule, right? Quotient rule says the natural log of 1 over e is equal to the natural log of the numerator minus the natural log of the denominator. What's the natural log of 1 equal to? And what's the natural log of e equal to? So this just simplifies to -1. So the natural log of 1 over e is equal to -1. In b, we have e raised to the -1/2 times the natural log of 16 power. They gotta be careful because you're dealing with, you have a natural logarithm in the exponent, right? So let's just look at the exponent. What can I do with that -1/2? Yeah, I can bring it inside the natural log and make it an exponent on the number 16. Then I'll have e to the natural log of 16 to the -1/2 power. Okay? So we have e raised to the natural log of 16 to the -1/2 power. So I'll make a note on this first example, right? What we used in this first example was the quotient rule. So you gotta be careful now, because -1/2 is the exponent on the number 16, and then natural log of 16 to the -1/2 is the exponent on the number e. Okay? So you gotta be careful here. Okay.
Could you repeat that?
-1/2 is the exponent on the number 16, And natural log of 16 to the minus 1/2 power is the exponent on the number e, okay? So we got like an exponent and an exponent, okay? So what I'm using here is the power rule in the exponent. Okay? I made this minus 1/2 an exponent on the number 16 in the exponent. Okay? Now, e raised to the natural log of 16 to the minus 1/2 power is equal to what?
16 to the minus 1/2.
Yeah, this can't, e and the natural log are inverse functions of each other, so they cancel each other. And we're left with 16 to the minus 1/2 power. Now, what property was that? That was property 4 on the previous page. Okay? Now you got 16 to the minus 1/2 power. What does the minus sign in the exponent mean?
Make it a fraction. Into a fraction.
Make it, what's the word I'm looking for? Give me an R. Reciprocal, right? Remember, minus sign in the exponent means reciprocal. So this is equal to 1 over 16 to the 1/2 power. Anything raised, what does anything be raised to the 1/2 power mean?
Square root.
Square root. So this is 1 over the square root of 16, which is equal to 1/4. So this that we began with is just equal to 1/4. Okay.
And is there a negative answer? You get negative answers for this?
For this problem?
Yeah.
No. No, the answer is 1/4.
Okay.
Yeah. Yeah, there, like, e raised to any number is positive, right? Because when we drew the graph, it was above the x-axis, right? It had no negative y values. Okay. Yes, ma'am.
Did you say that e raised to the natural log would cancel because of property 4?
This right here?
Yeah.
Because e and the natural log are inverse functions of each other, so they technically cancel each other.
Okay.
Okay. Any other questions? All right, let's take a look at C. We have log base 5 square root of 125. Now there's more to these problems. There's like more than one way a lot of times to solve them. And I'm always looking for the shortest route, but sometimes I end up taking the longest route to solve them. But you might recognize that 125 is equal to 5 cubed, right? And we're dealing with base 5 here. So 125 is equal to 5 cubed. And when you take the square root of something, that's the same as raising it to the 1/2 power, right? So the square root of 125 is the same as 5 cubed raised to the 1/2 power, right? Just a reminder, square root of x is x to the 1/2 power.
Right.
So we replace 125 with 5 cubed, and replace square root with 1/2 power. Now, 5 cubed raised to the 1/2 power, when you simplify that, that's 5 raised to what? 3/2, right? You multiply the exponents. So this is equal to log base 5 of 5 raised to the 3/2 power. Okay. Now, if you wanted to, you could use the power rule and bring the 3/2 down from log, couldn't you? And then log base 5 is equal to 1. Or you could recognize from these other properties, this is just equal to 3/2. I think the purpose of this example was for us to use the power rule. But it actually takes longer to apply the power rule than to do it this way. Okay? So this is property 3 from page 1 that we use. Which we used before already. Okay. Any questions on that? Yes, ma'am.
Is that the answer with the minus the log?
Oh, how did I forget that? Dadgummit. Alright. I was so focused on the first part, I forgot the second part. So what's log base 7 of 1 equal to? It's 0, right? From page 1. Log base 7 of 1 is equal to 0. The log of 1 in any base is equal to 0. Okay. So, this is equal to log base 5 square root of 125 minus 0, which is log, actually I could write it over here. Log base 5 of square root of 125 minus log base 7 of 1, and this is just equal. Log base 7 of 1 is just equal to 0. So when you subtract 0, you just let log base 5 of square root of 125. Okay? And then that is equal to 3/2. Okay? And this is equal to 3/2. Any other questions? Okay. All right, in D, we have log base 2 of 6 minus log base 2 of 15 plus log base 2 of 20. Okay. Well, here we have a difference of 2 logs in the same base. So we can apply the quotient rule in reverse. So in these rules, right, we can switch the left and the right-hand sides. So the quotient rule over here, when we switch the two sides, we have log base A of u minus log base A of b is equal to log base A of u over b, right? All I did was switch the left and the right-hand sides. So this difference in these two logs is equal to log base 2 of 6/15. 6 goes in the numerator, 15 goes in the denominator. And we add to that log base 2 of 20. So in this step, right, we use the quotient rule. Stay with me. Now we're adding two logs in the same base. And so we can apply the product rule in reverse. If I flip the two sides of the product rule over here, I have log base A of u plus log base A of b is equal to log base A of u times b. So applying the product rule, this is equal to log base 2 of 6/15 times 20. Does that make sense? All we're doing is applying the product rule in reverse. We're going from two logs to one log. Okay? And when we applied the quotient rule, we went from two logs to one log. Okay? Well, 6/15 times 20 is equal to 8. What's log base 2 of 8 equal to? 3. How do we know that? 2 cubed is equal to 8. And logarithms are just a fancy way of expressing that exponent, right? 3 is equal to log base 2 of 8. Okay. Any questions on that, ladies and gentlemen? Logarithms are fine. Okay. All right, so let's look at example 8. Now we're going to deal with the rules of logarithms involving variables. All right. So in example 8, it says use the properties of logarithms to simplify each expression so that the result does not contain logarithms of products, quotients, or powers. And so another way of saying the instructions is we're going to expand the logarithm as much as possible. So you might want to draw a line down the middle of the paper, right, to the left of B here, right, so that we don't mix the work up from the two problems. All right, so in the first problem, we have log base 10 of 5x cubed times y. Okay? So you should think of this, right? You're taking log base 10 of this entire quantity, right? It's not just log base 10 of 5, right? It's log base 10 of this entire product, 5 times x cubed times y. Well, product rule extends to more than a product of two numbers. Extends to product of 3 numbers, 4 numbers, 5 numbers, 6 numbers, 7 numbers, so forth. So this is equal to log base 10 of the first number, 5, plus log base 10 of the second number, x cubed, plus log base 10 of the third number, y. Product rule extends to more than a product of two numbers. It extends to product 3 numbers, 4 numbers, 5 numbers, 6 numbers, so forth. Can't do anything with this logarithm. Can't do anything with that logarithm. But this logarithm, we have x cubed in the argument. What goes inside the logarithm is called the argument. And so we have x cubed as the argument inside this logarithm. And that exponent 3, you know, can be brought down in front of the log. So this is equal to log base 10 of 5 plus 3 times log base 10 of x plus log base 10 of y by the power rule. Okay? Any questions on that? All right. So in 8b, we have another logarithmic expression to expand. We have the natural log of the quotient, x squared times the square root of x minus 3 in the numerator over the cube root of x squared in the denominator. And so we got to expand that as much as possible. Okay? You might be asking why are we doing this, right? What's the application? For those of you who have to take Calc 1, Math 120, right, we've learned about derivatives in this class. It's easier to differentiate a function like this after you expand it than to differentiate it the way it is right now. Okay? And so when we expand it, we're just rewriting this as, you know, what our final answer is equal to this. And so it's easier to differentiate this function when it's expanded than to differentiate it as it is, right? So there is application for this. So typically, when we have to expand a logarithmic expression like this, there's an order of applying the rules of logarithms that seems to work better than other orders. And the first one I like to use is the quotient rule. First, then the product rule, And then lastly, the, power rule. That order seems to work best for me, okay? So you notice that we have the natural log of a quotient. So by the quotient rule, this is equal to the natural log of the numerator minus the natural log of the denominator. So the natural log of the numerator is the natural log of x squared times the square root of x minus 3. And the square root of x minus 3 can be written as x minus 3 to the 1/2 power, can. Actually, you know what? I'm going to save that. We're going to do that, but in the next step. So we'll leave it as square root of x minus 3 for now. And then we subtract the natural log of the denominator. The cubed root of x. So that's application of the quotient rule. Now you'll notice that inside parentheses here, right, this is a product. And so this is a product of x squared times this square root. So the product rule says this is equal to the natural log of x squared plus the natural log of square root of x minus 3. So applying the product rule, we have the natural log of x squared plus the natural log of the square root of x minus 3. And now I'm going to write square root of x minus 3 as x minus 3 to the 1/2 power. Okay. And then we subtract from that the natural log of cube root of x squared. Now we talked about rational exponents. Cube root of x squared is the same as x raised to what power? 2/3, right? 2 is the power and 3 is the root. So this is natural log of x raised to the 2/3 power. So in this step we use the product rule. And now lastly we can use the power rule, right? This 2 that's an exponent of the variable x here, it can be brought down in front of the natural log. This 1/2 that's an exponent of x minus 3 can be brought down in front of the natural log. And this 2/3 that's an exponent of variable x can be brought down in front of the natural log. And so we have 2 times the natural log of x plus 1/2 times the natural log of x minus 3 minus 2/3 times the natural log of x. Now I would say stop there, but in our expansion we ended up with 2 like terms, didn't we? What are the like terms? Right? The natural log x is an apple. You got 2 apples minus 2/3 of an apple, right? And so 2 minus 2/3, same as 6/3 minus 2/3, which is 4/3, right? So 2 natural log of x minus 2/3 natural log of x is equal to 4/3 times the natural log of x plus 1/2 times the natural log of x minus 3. And hold it. Okay. I just have an error in my notes. So, taking math 120, you gotta differentiate this function. It's a lot easier to differentiate this function than that, right? So this in the box equals this, okay? But it's easier to differentiate this in the box than this up here. Okay? So any questions on that, ladies and gentlemen? Okay, so that's expanding, okay? Expanding the logarithmic expression. All right. So in example 9, on the next page, we have to find a logarithmic function f of x equals log base b of x such that the graph of f passes through the point 64, 3. So f of x, the logarithmic function, log base b of x, and its graph passes through the point 64, 3. X is the y coordinate, 64 is the x coordinate, 3 is the y coordinate. So we basically got to figure out what b is. Okay? What is b for this function? Well, first step, replace f of x with y. So we have y is equal to log base b of x. And now we use the point to put in for x and y. Y is 3. X is 64. I said earlier, every logarithmic function has an exponential function, right? And every exponential function has a logarithmic function. So remember, b is the base. 3 is the exponent. So what's the exponential equation that goes with this logarithmic equation?
E cubed equals 64.
Yeah, the base b raised to the third power has to equal 64. So b cubed has to equal 64. So some people use the word exponentiate to describe what we're doing. Okay. So it was back on example 3 on page 1, right, where you were given a logarithmic expression and you had to write the corresponding exponential expression. Okay. So that's what we're doing here. Here's the logarithmic expression. We're writing the corresponding exponential expression. Well, I wrote 6 cubed. That's supposed to be b cubed. Sorry. What does cubing? Cube root, right? So we take the cube root of both sides. Cube root undoes the cubing, and we're left with b is equal to 4, right? Because 4 cubed is equal to 64. So what's our logarithmic function that passes through this point? Put 4 in for b here. And you have f of x is equal to log base 4 of x. Any questions on that? So we did a similar type problem with exponent when we were doing exponential functions, right? Section 5.1. All right, in example 10, you're given a logarithmic function, and you got to find the domain of that logarithmic function. Well, see if I can find it. We talked about the domain of log functions back on page 2, right? When we did those two graphs. And what did we note? You can't take the log of 0 or a negative number, right? That's why the domain for log of x is only the positive numbers, right? X has to be greater than 0. So to find, but now, instead of just having x in the argument, is in the natural log function, we have a function of x as the argument inside the natural log function. So instead of setting x greater than 0, we have to set the argument x squared minus 1 greater than 0. Because that in parentheses can never equal 0, and it can never be less than 0. It always has to be positive, greater than 0. And now you got to solve for x. Okay? Well, we've solved these types of inequalities before. This is a quadratic inequality. And believe it or not, ladies and gentlemen, this is section 1.1 material. We were doing this in August. This is exam 1 material. Okay. You could have had this on an exam. On exam 1. And so, first step, you already got 0 on the right hand side of the inequality. So you factor the quadratic on the left, and it factors into x plus 1 times x minus 1. Actually, I left out a step. You set x squared minus 1 equal to 0. And then when we factor, we get x minus 1, x plus 1 times x minus 1 is equal to 0. Right? It's actually a difference of squares. And so you set the first factor equal to 0, the second factor equal to 0, and when you solve for x, you get x is equal to minus 1, and x is equal to plus 1. So the next step, remember the next step? You take the real number line for the variable x, and you use those two numbers to split the real number line up into intervals. Well, does minus 1 and 1, are they in our solution set? The answer is no, because plus 1 makes the left-hand side equal to 0, and you can't take the log of 0. And the same is true for minus 1. Makes the left-hand side equal to 0. So we got to put open circles on those two numbers. They're not in our solution set. And then we use the test point method to see if any of these three interval numbers are in our solution set. Does this all sound vaguely familiar? Right, this could be on the final, right? This could be a final exam question. And so test point for numbers less than minus 1, I use minus 2. And you can either use the factored form, right, or the unfactored form. And so I'll use the unfactored form. Minus 2 squared minus 1 is equal to 3. That's positive. So that means all these numbers up here to the left of minus 1 are in our solution set. Yes, sir.
Why are they both open circles again? Is it because that's
Because if you put in 1 in for x here,
okay?
1 squared is 1. 1 minus 1 is 0.
Oh, okay.
And
so
you can't
plug
take the natural log of 0.
Okay.
Same with minus 1. You put minus 1 in for x. Minus 1 squared is 1. 1 minus 1 is 0.
Okay.
You can't take the log of 0. 0 is between minus 1 and 1. So when I put in 0 in for x, I have 0 squared minus 1, which is negative 1. So any number between minus 1 and 1 makes x squared minus 1 an argument here, negative. And you can't take the log of a negative number. So none of those numbers work between minus 1 and 1. Then in this third interval, 2 is greater than 1. So I'm going to put 2 in for x, and 2 squared minus 1, which is equal to 3 again, which is positive. So any number greater than 1 will make x squared minus 1 greater than 0. So these numbers work. And so the domain minus infinity to minus 1, parentheses, because we're not including minus 1. Union 1, parentheses 1, to infinity. That is the domain for this logarithmic function. Okay. Those are the numbers you can put in for x here, and this function will equal a real number on the right-hand side. Okay. Any questions on that? Okay. So we'll stop right here, right, and pick it up tomorrow.